tonight. This is part of a two-week summer program for high school students that we've been doing for many years now. We have a special event in the evening of the second week. Last year we had a mini program, and so we didn't invite any speakers, but 2 and 3 years ago we showed the movie Particle Fever. I don't know if any of you have seen that. And we invited Nima Hamid, who's a very well-known and very distinguished theorist, to come, and also a star in the movie. And so we showed the movie from 7 to 9, and then Nima stayed from 9 until well after midnight, answering questions. So we hope to get you out by about 8:30 or at the latest 9 tonight, but perhaps our speakers will be willing to stay till midnight. No, maybe not. Maybe not. So anyway, tonight we're going to talk about a very interesting and very hot topic, which is some issue in cosmology, in that several measurements have been made of the Hubble constant by different methods, and they currently disagree. And so if that's really true, it means there's something we really don't understand about cosmology. The current standard model of cosmology is wrong. So I'm going to give about a 10-minute introduction to this. I'm not an expert, and then I'm going to turn it over to the 3 expert speakers. But first, let me just kind of try to set the stage. So, does everyone know what happened 14 billion years ago? What happened? The Big Bang happened. And many people have the impression that the Big Bang was an explosion. In fact, if you go to the Hayden Planetarium, to their Big Bang room, you know, the video seems to imply it was a big explosion. But it wasn't. What it was is that space began expanding. It wasn't an explosion, the space began expanding. It was an explosion, then it comes from one point, like a bomb going off. But this was an expansion of space everywhere. So everything in the universe is moving away from everything else. So no matter where you are, things are moving away from you. Okay? So here, for example, on this slide is the Milky Way, us, and then here's some distant galaxy. And so that galaxy, because of this expansion of space, is moving away from us. Now, what do you think it would be if you looked at a galaxy that was twice as far away? Would it be moving away at the same rate, faster, or slower? Speak up. Faster. Okay, why?
Space.
Huh?
Space in between.
Yeah. If we looked at a galaxy twice as far away, then there's more space between that galaxy and us. And so there's more space to expand. So if it's twice as far away, it'll be moving away with twice the speed. Okay? Now, here's a demonstration of this with a so-called Overman sphere. It's just a demo. It's not really very accurate. You may have seen one of these. If you go to the Liberty Science Center, there's a very big one of these. Okay? And so if I let this go, the sphere will expand, and on the sphere are stars. They should be galaxies. But I let it go, and you can see that no matter what galaxy you're in, all the other galaxies are moving away from you. Right? So this is an exact model. We're looking at a 2-dimensional surface here, and of course the universe is 3-dimensional. You should try to think of a 3-dimensional sphere, a 3-sphere, rather than a 2-sphere. But also this gives the impression that the universe is closed. And our best ideas now is that the universe is flat and not closed like a sphere. So this is not such a good model for that. The other thing is this expansion of the universe is very simple. All it is space expanding. Okay, the way this thing expands is very complicated. Right? It'd be a very complicated mechanics problem to figure out how this thing is expanding. But anyway, it shows you that no matter where you are in the universe, things are moving away from you. And the further away they are, the faster. So that's quantified by the Hubble constant, which is what we're going to talk about tonight. The Hubble constant is simply the velocity of some distant galaxy, its velocity away from us, from the Milky Way, divided by how far away it is. Okay, and that's one of the main parameters in cosmology to know, to be able to measure and get the value of. Okay, so today we have what's called a standard cosmology. It's called the lambda CDM cosmology. It was built up, well, certainly over the whole 20th century, but mostly since the 1970s. Since then, we learned about dark matter and we learned about dark energy. And so those are now incorporated into the standard cosmology. And here are some, most of the important parameters of this cosmology. Well, one is the age of the universe when the Big Bang happened, and that was 3.8 billion years ago. And then the Hubble constant that I just mentioned, the value of that we'll debate tonight, but roughly it's 68. All right, I don't know why it's marking. It's roughly 68 kilometers per second per megaparsec. Now megaparsec is astronomer speak. A megaparsec is roughly 3 light years. So it's about 68 kilometers per second per 3 light years. Per 3 billion light years. So if a galaxy were 300 billion light years away from us, then it would be moving away at roughly 7,000 kilometers per second. Pretty damn fast. Then the other parameters that govern the rate of expansion of the universe are these omega parameters. And so the one on the left, omega m, is due to the density of matter, ordinary matter, and that accounts for about 5% of the expansion. And then there's a parameter due to the density of dark matter. We don't know what dark matter is, but we know its density, and that's contributing 26% to the expansion. And then omega lambda is the contribution due to dark energy, or the cosmological constant, or the vacuum energy density. They all mean the same thing. And it's the dominant one. It's contributing about 69% to the expansion of the universe now. And that's why the expansion of the universe is accelerating. And then there's a term that could come from the curvature of the universe, but that's approximately 0. So it looks like the universe is probably flat. It's not curved either positively or negatively. Okay, so these are important parameters, and they'll probably come up in the talks tonight. And then, so here's what we're going to talk about. This is a measure of the Hubble constant. The horizontal axis is a Hubble constant. On the right, with the lines in red, are the values measured for the Hubble constant by looking at distant galaxies, type 1a supernova. And you'll hear about that tonight. And so they're clustered, I don't know, around 72, 73 values of that. Whereas another measurement that comes from measuring the anisotropies of the cosmic microwave background radiation is different. I can't see from here, but maybe that's around 68. You can see the difference. And the difference between the measurements with the type 1a supernova and the ones with the CMB differ by 3.4 sigma, 3.4 standard deviations. So that means if the values are correct, and maybe one or other of the groups have made an experimental error, but if their values are correct, and if they've correctly estimated their error bars, maybe they haven't, but if they have, then it means there's 1 in 3,000 chance that this difference could be due just to random statistics. Okay? So it's possible, 1 in 3,000, but if they're really correct about their values and about the error bars, then something strange is going on. It's not understood now. We'll hear more about it tonight. And this is a really big issue in cosmology. Okay, so that's all I have to say. So let me turn up the lights and introduce the speakers. I'm going to introduce you all at once, and then you'll just come up one by one. So our first speaker is going to be Saurabh Jha. And sorry, I have to get my notes. I didn't memorize your bios. So Saurabh Jha is a professor here at Rutgers, professor of astronomy. His research focuses on studying exploding white dwarf stars called type 1a supernovae, I've just been mentioning, and using them as cosmological tools to survey the universe. He's a New Jersey native. He graduated from East Brunswick High School. Anybody from East Brunswick here? Okay. It's close by. He received his PhD in astronomy in 2002 from Harvard, and then he did postdoctoral research at UC Berkeley and at SLAC, and he joined Rutgers in 2007. So he was a member of the team, as a graduate student at Harvard, he was a member of the team that discovered the accelerated expansion of the universe, one of the 2 teams. And he's been working on that ever since, so he's one of the world experts in it. He himself didn't get a Nobel Prize, his advisor got one of the 3 Nobel Prizes, but he did get a trip to Stockholm. So close, but not... Yeah, and he's a co-recipient of the Gruber Cosmology Prize. That's not the Nobel Prize, but it's very high up. And also the Breakthrough Prize in Fundamental Physics, which is a really big prize in physics that started about 5 or 6 years ago. Okay? Then our second speaker is Matthew Mahavacharo. He's a postdoc at Princeton University. He did his undergraduate work at Delhi University, and his master's, he got a master's from Cambridge in the United Kingdom, and then got a PhD from Stony Brook. And his PhD was on constraining dark energy using the cosmic microwave background radiation and galaxies. He's currently a postdoctoral research associate at Princeton in the astrophysics department, and he'll soon be joining the Perimeter Institute in Waterloo, Canada, a really major institute, as a People's Fellow. And then our third speaker is Matthew Buckley. He's also a professor here at Rutgers. He's a theoretical astrophysicist, and he studies, he studied physics and mathematics as an undergraduate at Kenyon College in Ohio, and he earned his PhD in theoretical physics at the University of California at Berkeley. His primary interest is in dark matter, what it is, what the signatures from it might be, how best experimentalists might go about detecting it. But he's also an expert in gravitational waves, and that's what he's going to be talking to us about tonight. Okay? So then, one more thing before we start. So I'm going to dim the lights. We're going to be talking about measuring redshifts to measure the velocity of galaxies away from us. And that's based, the instrument used is just a sophisticated version of what I'm going to try to show you here. So here we just have a filament light, incandescent bulb, and down here is a hydrogen tube. Okay. So we excite the hydrogen gas, and then it emits photons as it goes back to the ground state. So first, you use your glasses to look at this light. Okay, and you see a spectrum, right, like a rainbow. Right? That's because this incandescent light is giving off light of many different frequencies, the so-called black body spectrum. So you don't see any spectral lines, it's just a continuous spectrum. But then let me turn this down and then turn on the hydrogen. And now compare it with, if you look at the hydrogen, you see lines off to the side, right? Everybody see it? Yes. And you can compare the lines to the continuous spectrum in the incandescent bulb, although you might be able to see it better if I turn this bulb off. So those spectral lines are photons corresponding to the energy difference between levels in the hydrogen atom. So this is like a fingerprint of hydrogen. If you see this set of spectral lines, you know you're looking at hydrogen. But now, with the hydrogen in a distant galaxy, that galaxy is moving away very rapidly. Well, no, I take that back. If the galaxy is far away, then the space between us and that galaxy is expanding by a lot. So while the photons are traveling from the galaxy to us, space has been expanding. That stretches the wavelengths of the photons and redshifts them. So you can look at the spectrum from some atom like hydrogen, you'll see the spectral lines, but they'll be shifted to lower wavelengths. And by measuring the amount of that shift, you can tell how fast away they're moving. So measuring the redshift, which is a major measurement in cosmology, is really based upon this simple principle of using diffraction gratings like these. Okay, so that's enough. I took way too much time. So, Sarah, yeah, lights on.
Okay, thanks Steve for that introduction. That really covers a lot of the groundwork for what I'll be talking about, and subsequent speakers, I guess. So what I'm going to talk about is one, so you saw there were these two measurements of the Hubble constant and they disagreed with each other. And the way we're going to do this is that for the three talks, I'll talk about one side, what we call the local cosmic distance ladder, or measuring the Hubble constant locally using type 1a supernovae. I'll explain what that is. Matt will talk about, well, Matt number one will talk about the cosmic microwave background and how we measure Hubble constant, or we infer the Hubble constant from those measurements. And since those are in disagreement, the other Matt, Professor Buckley, is going to tell us about maybe a new way of reconciling those, a new way to make the measurement that might solve the problem. So that's what we have in store for tonight. So what you're looking at here are pictures of two relatively nearby galaxies. They're both in the Messier catalog of galaxies. This is M101. and this is Messier 82. And in these galaxies, in the past few years, we had an exploding star in each of the galaxies, a supernova, and a particular kind of supernova, a type 1a supernova. Nicely here, there are arrows pointing to them, but actually in the sky there aren't these arrows. There are actually a lot of people who go and take pictures of these galaxies over and over, looking for the new supernovae and telling everyone about them. So that's a major enterprise in astronomy, and it includes even amateur astronomers. So that's a kind of fun thing to get into if you're interested. But so they're pointing at these stars, which are exploding stars in those galaxies, and they're of a certain kind where we can use them, the fact that they appear, we can use their light to tell us how far away these galaxies are. And so that'll play a role in the story today. So you saw in the equation that Professor Schnetzler showed that the Hubble constant is a pretty simple measurement. It's a velocity, so you have to measure the velocity of something, some distant galaxy. And you saw in the demo how we do that. Just using the Doppler shift of light, we can measure the velocity, the redshift of a galaxy. That's actually pretty easy. That's the easy measurement. The hard thing to do in astronomy is measuring distance. Okay? So this is a picture of the night sky. Does anyone recognize this constellation? Orion, yes. So this is the constellation of Orion. And then the dog star here, Sirius. And you might look at these stars in the sky and say, okay, well, the way we look at the sky kind of looks like it's 2D, right? Everything is just projected onto a screen. And well, here it literally is 2D. But in the real universe, it's in 3D. And you kind of might wonder, well, what are the distances to these stars? Are they all the same plane? Are they all the same distance from us? Or not? Okay? And you might think, well, how would I be able to tell what are the distances to these stars? And so one thing you might think is, well, I can see that some of the stars, like this one and these here, Betelgeuse, they seem brighter than some of the other stars. And you can even see lots of fainter stars in the background. So maybe if all stars were the same, then I could just use the fact that some are brighter, and that would tell me that those are closer. So that's what's called a standard candle in astronomy. The idea where you have some object which is the same everywhere, and so that you can use the fact about what it looks like to you, which ones are brighter, which ones are fainter, to figure out how far apart they are, how far away they are. Okay? Unfortunately for stars, that doesn't work. So if you actually measure the distances to these stars, and here I've labeled some of them. So for Betelgeuse, the distance is about 640 light years. For Bellatrix, which looks a little fainter than Betelgeuse, okay, it's actually closer though. It's only 250 light years. Okay? Rigel, 860, SAFE, 650. The belt stars there are all different distances, even though they're very close in the sky, they're not all at the same distance. Okay? And just by looking at the light from these stars, you wouldn't be able to figure out what the distances are, unless you knew more about what kind of star it is. Okay? And the reason is that stars aren't all the same. Stars aren't all like the sun. There are some stars that are much brighter than the sun, and then there are stars that are much fainter than the sun. And so if you don't know how intrinsically bright a star is, you won't be able to measure its distance just by looking. There's one more star here, Sirius. Does anyone know how far that is? Just, looking at this and any guesses? Any ideas? How many people say that it's farther than, let's say, Betelgeuse? How many say closer? Most people say closer? Yeah, it's way closer, someone said. That's exactly right. It's only 8.6 light years away. But actually, if you put it at the same distance as Betelgeuse, it would be way, way fainter than Betelgeuse. It just happens to be close to us, that's why it looks bright. Okay. So this is a problem with measuring the universe in 3D, that stars are all varying, of varying luminosities, varying intrinsic brightness, so we can't use how bright they appear to measure their distance. Okay. So people throughout the history of astronomy have been trying to figure out a way, can we figure out some objects in the universe where we can use the fact that they're all the same or all very similar to measure their distances, looking for these standard candles. And one of the best standard candles we have is thanks to Henrietta Swan Leavitt, who studied a particular kind of star in a nearby galaxy called a Cepheid variable star. So a Cepheid variable, like the name implies, it's variable, it changes its brightness over time. And so the light of a Cepheid goes brighter and fainter, brighter and fainter. Okay? And there's a period to that. The period is usually measured in days, so maybe 3 days or 10 days or 100 days, how long it takes to go up and down in brightness. What Henrietta Leavitt found, and now what we call the Leavitt law that she published in 1912, was that the brighter, the intrinsically more luminous Cepheids take longer to rise and fade, whereas the fainter ones go faster. So if you were to observe a Cepheid variable star, see how fast it took to rise and fade, you could figure out exactly how bright it is. If it took 10 days, then you would say, aha, that star is about 3 times the brightness of the sun. Or if it took 100 days, you would say, aha, it's 30,000 times the brightness of the sun. Okay? So that gave us a way to turn Cepheids into standard candles, into figuring out what their luminosity is, how bright are they truly, and then from that, based on how bright they appeared to us, we could tell how far away they are. So Cepheids became one of the big tools in our astronomical arsenal to measure distances to other to these stars. And the person who used this tool to great effect was Edwin Hubble. Okay, so this is Edwin Hubble looking at a picture of our nearby neighbor galaxy, the Andromeda Galaxy M31. And he's actually pointing at a star there, you can't quite see, but he's pointing at a star which he found to be a Cepheid variable star, like the kind that Henrietta Leavitt studied. And so he took observations with the Palomar telescope of that star over time, measured how long it took to rise and fade, and figure out how far away that galaxy was. In fact, he figured it out that it was a separate galaxy. Till then, there was actually a big debate whether these fuzzy nebula-like things in our sky were separate galaxies, separate from the Milky Way, or within our Milky Way. But because he was able to measure the distance using the standard candle, he figured out that Andromeda was a separate galaxy. Okay, he did more than that. He started using these techniques to measure distances to lots of galaxies. And with some help from previous observations, people had measured the velocities of those galaxies. And he did once you have two columns of numbers, he did the first thing that you could think of is make a plot of them. So he plotted the velocity of the galaxy measured from the Doppler shift, like we saw before, and the distance using techniques like the Leavitt law on the x-axis. Okay? And he measured his distances in parsecs, or actually you can see this is millions of parsecs. So we talked about 1 parsec is 3.3 light years. His velocities, actually on his plot, he messed up. This is actually the plot from his paper. It should say kilometers per second, but he wrote down kilometers. If one of my students did that, I would take points off for this kind of assignment, this kind of work, but Hubble gets a telescope named after him. Standards have changed. And what he noticed though, when he plotted these things, the velocity, the speeds of the galaxies, one thing that people had noticed already was almost all the galaxies were redshifted, they were moving away from us. That seemed kind of strange. If you get on a bus and everyone suddenly moves away from you, then probably time to take a shower or something like that. But all the galaxies in the universe seem to be moving away from us. And what he found is that it seemed like there's a straight line relationship. The farther away a galaxy is, the faster it's moving. And we can explain that in terms of the expansion of the universe, just like you saw. So the slope of this relationship is what we now call the Hubble constant. Hubble was not vain enough to call it the Hubble constant. He just called it K or something. You can see that the correct units of the y-axis are kilometers per second. The units we like to use for the x-axis are megaparsec. So when you make the slope, it's kilometers per second per megaparsec. It's kind of a funny unit. There's 2 units of length in there. You could even cancel them. But these are the traditional astronomy units we use for this number. And if you actually read off the numbers on this plot, the estimate that you would get from Hubble from 1929 was 550 kilometers per second per megaparsec. And the modern value that we're kind of going to debate is maybe 66 or 67 versus 72 or 73. Okay, so that's what we're going to talk about today. Hubble is way off. Okay? It turned out what he thought were Cepheid variables in some of the galaxies were not actually Cepheid variables, and he made a bunch of mistakes on the distance axis. The velocities are all basically right, but the distance axis was off by a factor of 8 or so. All right, so what is Hubble's law? What is it telling us? Well, you saw a demonstration with the Hoverman sphere, but here's kind of an animation of that. Okay? So imagine we live on this galaxy marked A, and the universe is expanding, and we look at that over time. What we see is that the galaxies have moved relative to us. Okay? And the farther apart they are, the more they move. So in other words, if you measure instantaneously, the farther they are, the faster the speed. Okay? So that's Hubble's law. It's a consequence of the expanding universe. And notice it didn't matter if we were on this galaxy, galaxy A or galaxy B, everyone would see the same Hubble's law. Everyone would see the same Hubble's constant. The rate at which the galaxies are expanding away from us is the same for all observers at the same time. Okay, so people since Hubble's time have been trying to measure this rate of expansion, the Hubble constant. And I told you that Hubble was getting, so this is versus the time. Like this is not the Hubble constant changing with time, this is people's measurements of the Hubble constant changing with time. So how good we were doing trying to measure this number. So you can see Hubble's value, and there are actually other people, there was one person, Lemaitre, before Hubble, but you didn't really recognize what he was onto. Anyway, there are a bunch of values early on which were in these 500s. Then people realized they were making mistakes about the distances, that in fact there are actually 2 kinds of Cepheid variables, stuff like that. And so that brought the numbers down until you get to sort of the 70s and 80s when people started to converge a little bit at least, and their estimate of this number. Okay? Actually, for most of the 80s, there were two camps. Some people who thought that the number was close to 50, and some people who thought the number was close to 100, and they really fought it out. They would have conferences in rooms like this, and one person would get up, and then the next person. So we're going to recreate that with less animosity today. There was a lot more animosity back then. Okay. And so here's a zoom in of the latest part of this, where it's since 1996 or so, and you can see that the numbers are mostly converging to around, somewhere around 70. Okay. So in fact, one of the key aims of the Hubble Space Telescope, so named after Edwin Hubble, one of the reasons it was launched was to measure the Hubble constant to an accuracy of 10%. And so in the early 2000s, the Hubble so-called Key project, of which one of my advisors, John Huckrow, was part of, came out with a paper that said the Hubble constant is 72 plus or minus 7 in these units. And so they succeeded in measuring the Hubble constant to 10% accuracy, 72 plus or minus 7. So that was a great leap forward since the days of 50 or 100, but we want to do better since then, and that's what we've been trying to do. Okay. So since then, you can see most of the measurements around 70-ish, and now we want to see how well can we pin down this number. Okay, so what is the modern way of doing this? We use what's called the cosmological distance ladder. And the idea of a ladder is you have these different rungs, and you build one technique on top of the other technique. Okay. So if you want to measure distances in the universe, well, first you'll have to measure distances in our own solar system. You'll have to figure out how far away is the sun, how far away are the planets, for instance. Okay. That's relatively easy. You can take a radio wave and just shoot it at the sun, wait for it to bounce, come back to your receiver, and just time how long that took. And if you know the speed of light, you can figure out how far away is the sun, how far away are all things in the solar system. Okay. The problem is you can't do that for nearby stars, because nearby stars are light years away. You'd have to wait years for the signal to come back, and even our students don't have the patience to do that kind of experiment, even if we had powerful enough transmitters to do it. Okay. So you have to come up with some other technique that lets you measure the distances to nearby stars. Okay? And the way the ladder works is, well, if you know the distance to the sun, then you can set up a triangle like this and use another technique called parallax. Since we know this distance, the base of the triangle, if we can measure the angle that a star seems to shift as the Earth goes around the sun, then we'll know the distance to that star. So that's why it's a ladder. It builds on the previous rung. Okay, so this technique of parallax allows us to measure distances to relatively nearby stars, maybe thousands of light years away. I'll talk a bit more about that in just a second. Okay? And then there are other techniques like the Cepheid variables and the type 1a supernovae I'll talk about, which let us go farther and farther with this kind of cosmological distance ladder. So normally when I give this talk, I would kind of end there, but we've had huge advances actually in all of these fields recently. And one of the really cool things is this satellite that was launched by the European Space Agency a few years ago, and just a few months ago had its first really big data release. It was actually called Data Release 2, but it's the first one that had lots of data for us to measure distances to stars. So the mission of Gaia was to measure parallaxes of lots of stars in our galaxy. And so this is a picture of the spacecraft. This is actually not an image taken by Gaia, but this is just a map of wherever Gaia found a star, you make little points. And so Gaia was surveyed over 1 billion stars, so there are over 1 billion points on this map. And you can see that most of the points are not just randomly scattered, most of the points are in a plane. That's our Milky Way galaxy. There are a bunch of points over here. That's one of our neighbor galaxies, the Small Magellanic Cloud. There's the Large Magellanic Cloud, etc. So these are just all the stars that Gaia sees. But Gaia wasn't just making a map of stars, it actually watched the stars move as Gaia orbited around the sun. Okay? So I don't know if you can see it here. Can you see those stars shifting? Okay, those are the positions of those stars as they appear to move as Gaia orbits around the sun. And you can see that some of them wobble quite a lot, and then some don't seem to wobble very much at all. And the ones that are close to us will look like they move a lot more, and the ones that are farther away won't look like they move very much. You can do this experiment yourself. If you hold your finger in front of your face, and you close one eye and close the other, and you go back and forth, you can see the finger appears to wobble. And if you move your finger farther away or closer, you'll get either a bigger shift if it's closer, or a smaller shift if it's farther away. That's exactly what Gaia was measuring. Now, to make this little movie, they had to exaggerate the effect 100,000 times. Okay, so the shifts were actually really tiny, but Gaia was able to measure. So Gaia has really nailed measurements of parallaxes throughout our whole galaxy. So, and we're going to get more and more results from Gaia over the next few years. So this is already one revolution. Okay, what if we want to go far away from us? not just nearby, to the end of the distance ladder over here for things even far away. So the best thing to use right now are type 1a supernovae. So this is what I study, exploding white dwarf stars. So white dwarf stars are the end stages of some kinds of stars. So the sun is going to end up its life after about 6 or so more billion years as a white dwarf. Right? And normally by themselves they would be pretty stable, but it turns out there's a maximum mass limit to a white dwarf. And if you get close to that mass, something exciting might happen. And so one way to get a white dwarf to be very massive is for it to have a companion star, which can dump material onto the white dwarf and perhaps make it explode. So exploding white dwarfs are what these things called type 1a supernovae. So supernovae are exploding star. There are a few different classes of exploding stars. So this kind is called type 1a. They're the exploding white dwarfs. Okay. So here's a picture of a nearby galaxy. This is actually one I worked on for my PhD thesis. Here it is in May of 1998. Does anyone see any difference between those two pictures?
Yeah.
Yes, you see one star in that galaxy, which was one white dwarf that you couldn't even see before, has exploded, and suddenly, for a short period of time, that star is as bright as 10 billion stars. So what's really great about these, they're interesting phenomena on their own, these exploding white dwarfs, but what's really impressive is that they turn out to be very good standard candles. Just like the Cepheids that Henrietta Leavitt understood, people since the 90s have been understanding that type 1a supernovae also make excellent standard candles. They're a lot rarer than Cepheids. Cepheids are a lot more common in a galaxy. In a galaxy, you might have hundreds or thousands of Cepheids going on at one time, whereas a type 1a supernova might take 100 years to go in a regular galaxy. Okay? But the flip side of that, even though they're a lot rarer, they're much brighter than Cepheids. They're about 1,000,000 times brighter than a single Cepheid star. So that means you can see these type 1a supernovae much farther away, about 1,000 times farther away. And so we can measure distances to billions of light years away using these type 1a supernovae. So we've been doing that for a long time, and this is a long story. I usually give a whole talk just on this slide. But one of the things that Professor Schnetzer mentioned is we used these type 1a supernovae to measure distances to galaxies billions of light years away to see what the expansion of the universe was doing billions of years ago. And we were surprised that the expansion of the universe was actually slower billions of years ago than it is today. That the expansion is speeding up. That's not what people expected. So this is the accelerating universe. It led to a Nobel Prize again, not for me. But for some people on my team in 2011. And so this is the lambda in the lambda CDM that we'll talk about in standard cosmology, this dark energy, this accelerating expansion of the universe. So that uses supernovae very far away. But for the Hubble constant measurement, we actually look at supernovae relatively nearby. So this is a compilation of supernovae that I also made in a paper. This is 95 type 1a supernovae. Here's the velocity of their galaxies in kilometers per second. They fixed the units. And the distances in megaparsecs. And you can see, Hubble was right. The nice straight line does a really good job of fitting these data points. Okay. One thing to notice is, V is equal to h times d. That works really well. This gray box here, that's Hubble's original Hubble diagram. It would have fit in there. Okay. So we've really expanded the range where we can test these measurements. And the value that we got in 2007 was, for this slope, is 73 plus or minus 6. Okay. And since then, we've been trying to improve the results. Nowadays, our best guess is somewhere around, or actually in 2011, our best guess was about 73.8 plus or minus 2.4. Okay. You can see that uncertainty, the error bar, keeps decreasing. That's what we're trying to keep working on, keep making more and more measurements to improve that. Okay. So how do we do that? I'm not going to go through the details of this diagram. But this is our modern cosmological distance ladder. It has 3 parts. So we use some kind of geometrical technique like parallax for the first rung. Then we use Henrietta Leavitt's Cepheids for the second rung. And then we use type 1a supernovae for the third rung. And we connect them all together and make our best distance ladder. And when you do that, the answer that you get for the Hubble constant is about 73.24. We have to give a lot of digits of precision now that we're getting so precise. A more recent update has moved it to about 73.5. But anyway, it's changing a little bit. Our best estimate was to be something around 73 plus or minus 2. Okay. There are a lot of ways you can mess up this measurement. So there's a lot of things you have to worry about with everything calibrated perfectly as you make observations of Cepheids and supernovae. Does everything line up? So we tried to see how could we have messed up. And so instead of just one measurement, we looked at all different ways. I don't want you to go through the whole list, but we looked at all different possible ways that we could have messed up and tried different choices of how we compare things. And if you look at the numbers here, they don't change that much. 73, maybe down to 71.7 to 74-ish. So in that range, 73 plus or minus 2 seems to encompass that whole range of our measurements. Okay. So this is the issue. So here is our measurement from what's called the SHOES project. It stands for supernovae, Hubble constant, and some other words I forgot, led by Adam Rees. Here's our measurement, and this is what Professor Schnetzer showed from the CMB that Matt will talk about next. Okay? And there's an offset. Here's our measurement. There's there with the error bars, and they're offset by some amount that we need to say, is that a problem or not? So just yesterday, actually, just yesterday, the Planck team, which measures the CMB, just released its new paper, its 2018 results. The previous one was from 2015. And so here's the value now. So you're seeing hot off the press, updated in the last half an hour before I made this slide, data with their new result. But you can see it's still off from the measurement that we made with the super. Okay. Maybe we messed up, and so we thought, okay, well, let's look at other people who have tried to measure the Hubble constant nearby using different techniques. And you can see our error bar is small, but there are some other methods that have larger error bars, but they are generally consistent with our value. This one is a bit low, but these other techniques, so for instance, one is using gravitational lensing, that's a very common one, that's down here. If you average all of these together and just compare, you can see it's pretty consistent with what we do. So how can you explain this discrepancy between what we measure locally and what the CMB measured? Well, it turns out the CMB, it's not a direct measurement. You'll hear a lot more about this. It assumes that we understand what's in the universe. It assumes that those omegas that you saw before, that Professor showed, were all the major components of the universe. If you were able to change that, if you allow new components to the universe, and I won't go into the details of what all these could be, but new physics, the kind of exciting topic where we didn't understand all of physics, then there are ways to maybe bring these two measurements into agreement. So the big question is, did we just mess up? And so the disagreement is because either we messed up or the CMB is giving the wrong answer for some just simple reason we just messed up our experiment. Or might there be some new physics in the universe that's at work? So that's what we really want to understand. So since this is kind of such an important topic, people have been looking at lots of different ways to say, where could you have messed up? Oh, you did this wrong, you did that wrong. And so in blue are a bunch of different analyses of that result from a bunch of people trying different things out. And I don't go through the whole list of all the different possibilities, but you can see that the blue points mostly are consistent. We don't see any clear deviation. I won't talk about this. I think maybe Matt will talk about the different ways to look at the CMB measure. One thing I'll point out just because I'm on this paper, so one thing we did, for example, so one thing we might worry about for when you observe the light from a supernova and assume it's a standard candle, what if some of that light was just blocked by something in the way? Actually, if you look at these galaxies, you can see here like this dark part of the galaxy, or in this galaxy you see these light and dark parts. Those dark parts are caused by something called interstellar dust. Small particles in the interstellar medium that can